Each one is over 1,000 feet long, weighs almost 100,000 tons,
That's a serious elevator.
and costs $3.5 billion.
We caught one.
For 40 years, Nimitz-class aircraft carriers have delivered U.S. military might all over the globe. But now, these legendary ships are being phased out to be replaced by new carriers. Before they're decommissioned, I'm going aboard a flagship vessel.
I never want to sleep under a flight deck again.
So I can uncover the engineering innovations that allowed this ship to launch, land, and relaunch more planes more quickly than ever before.
Now that was some serious engineering.
And see what made the Nimitz-class super carriers. I'm Chad Zdenek. I spent 7 years building rocket engines for NASA. Now, I'm taking things apart, breaking down giants of engineering piece by piece, so I can discover what made them legends of their time. Naval Base San Diego, home to this Nimitz-class aircraft carrier, one of the U.S. Navy's biggest warships. This will be my home for the next 5 days. I'm on board the USS Carl Vinson, and for the next week, I'm going to be working with engineers, mechanics, and sailors and show you some incredible pieces of engineering that keep an aircraft carrier like this operational. President Nixon wrote the check for the Carl Vinson back in 1974 for $3 billion. Construction began in 1975 under President Ford. In 1980, the new ship was launched under President Carter. In 1982, it finally entered service under President Reagan. And in 2011, under Barack Obama's presidency, the body of Osama bin Laden was brought on board for burial at sea. For 40 years, it's been the ultimate symbol of American military might. An enormous floating, plane-launching machine, bigger and stronger than anything that came before.
The carrier, fully loaded, maxed out, 97,000 tons. It's a pretty heavy piece of gear. The entire engineering suite that it takes to get this ship through the water, back and forth over 25 years, it is just an engineering marvel.
Now, this giant piece of engineering is on its way out. One by one, the Nimitz-class carriers will be decommissioned to make way for the Ford-class, raising the bar all over again. But you don't replace a $40 billion fleet of aircraft carriers overnight. That will take 30 years. In the meantime, the Nimitz ships have to stay on the cutting edge with constant upgrades and upkeep from a highly specialized mechanical crew. Each one of them trained in the extraordinary engineering that keeps this ship running. Now, I'm joining them as the ship heads into the Pacific to undertake a special mission. Testing pilots on their ability to take off and land on a carrier, hoping to win their final qualification, the last step in a naval aviator's basic training. I'll work with the engineering teams above and below deck to reveal the engineering innovations that make it all possible. The incredible catapult system that can launch a jet in just 2 seconds. The mighty elevators designed to get 35 tons of aircraft on and off the deck in seconds. The arresting system that uses cables and hydraulics to stop jets as they scream in at 150 miles an hour. And the giant flight deck, designed to allow more takeoff and landings than ever before. Day one of my time on the USS Carl Vinson. And my first job is one done by every seaman who ever served on any ship. Removing deck debris. It's got to be done as regular as clockwork. And on a carrier, it's more important than ever.
So right now, we're doing the everyday, twice a day. Basically, they get everyone on deck to comb through arm's length distance, and they're scouring the deck for any FOD, foreign object debris. When these jets are coming in, taking off, there's so much suction from the engines that they'll suck things off of the deck, go into the engines, and could cause some serious damage. So we gotta check it twice a day, every day. You wouldn't think that there'd be FOD on this deck. The wind's about 40 miles an hour. And this is what I found, a piece of wood, little piece of some sort of textile material, but I also found a small rock.
The basic job of an aircraft carrier is to take planes wherever they're needed and then launch them into the sky. On the USS Carl Vinson, that's done using a giant catapult. Or maybe not so giant, at least not from up here, where all you can see is the 2-foot shuttle sticking out of the flight deck like a shark's fin. Somehow, this tiny piece of steel has to fling a 30-ton jet into the sky at 150 miles an hour. The simple but incredible engineering behind this launching system is the result of a 100-year evolution of the aircraft carrier. That began in 1920 with the USS Langley. It was a coal ship, until naval engineers bolted a wooden deck on top, converting it to the US Navy's first ever aircraft carrier. Its job? To launch planes into the air from the middle of the ocean, using a runway a little over 500 feet long. Biplanes like these were made of wood, steel, and fabric. They weighed 2.5 tons, light enough to launch without the need of a catapult. A good headwind was all it took. But a fully fueled, fully loaded F-18 is 10 times as heavy. To get these planes into the air in just a few hundred feet, the Nimitz carriers needed huge power and a way to deliver it suddenly and at great speed. I love the solution engineers came up with. They turned to an age-old technology, steam. One of the things I've always been fascinated by is engineering innovation, and steam is a perfect example of that. It helped us in the Industrial Revolution, and now today, on the USS Carl Vinson, we're using it to catapult F-18s off a flight deck. And through all that, the basic properties of steam, they've stayed the same. When water is heated into steam, it expands in volume over 1,000 times. It's a law of physics that engineers first mastered in the 18th century when they used it to create the piston engine. The system that runs it is deep below decks. The start of our steam system all starts right here. Just beneath us is the power plant, and all that steam comes up through this giant duct, and it's actually fed through into our steam fill room right in here, where we've got 3 control valves to keep that system pressurized at just the right amount. Now, believe it or not, there's 3 other rooms just like this. What you see here, this is only for catapult number 2. The steam for each catapult is stored in 2 giant cylinders and pistons, each about as long as a football field. The pistons are connected to the catapult shuttle on deck. To launch a plane, the pressure is suddenly released, driving the piston and catapult forwards at 150 miles per hour. There are actually 4 catapults on board. Each has its own engine room and dedicated crew above and below the flight deck.
Hey, stand by real quick.
Hey, Truman. Hey, can you turn on the throttle tension?
What you got? You're at 5-0? Copy. Go ahead and meet a backup, bro.
When they get the signal, they fill these pipes with steam and bring it to pressure, arming the catapult. Then they wait for the signal that will shift a 35-ton fighter from standstill to 150 miles an hour in just 2.5 seconds. It's a system that leaves no room for error, which is why it gets tested twice a day, every day.
In just a few minutes, I'm going to be able to witness a no load from the catapult. It's basically when they test the catapult before any day they're doing operations with no load on it. This thing's going to fly by us at about 150 miles an hour, and I get to be 2 feet away.
Pilots' lives depend on this engineering working perfectly, which is why crew go through this routine so carefully. That's why you want to stay behind the foul line.
So we're loading up right now. We're bringing back the catapult. This is a safety line, foul line. Everyone's got to make sure that they're standing behind it, and then we're going to launch this all the way down. Now that was some serious engineering. This catapult blowing by at 150 miles an hour, and at the end, all you see is a bunch of steam coming up, and then a big splash, which is the water break at the end of the deck.
The no-load tests are complete, and everything is ready. Now, this trainee pilot is about to launch his aircraft for the first time and be tested on whether he's got what it takes. It's just the first in 5 days of tests and evaluations. At the end, he's hoping to have done enough to win his aircraft carrier pilot qualification. Once the catapult fires, the pilot needs to accelerate explosively to get the plane airborne.
There is a lot that could go wrong on the deck. We talk about it, we brief to those emergencies, and you have to trust your training as well as all the training of the flight deck crew to do their job and to do it well.
The pilot's launch is controlled from a pod built into the deck, known as the bubble. Once the catapult fires, it's impossible to abort takeoff. The pilot's along for the ride.
We're in the bubble, and we're launching off of Catapult 4, and the wings are literally coming right over our head.
Inside, the catapult officer, or shooter, makes the precise calculations necessary for a perfect launch. Each plane's standard weight is added to its load.
72, set metro to confirm on 4. Lights, no lights, -4. Thumbs, head steady, deck steady, no interval. So what we're doing is we're taking the weight from the aircraft, and then we put it into our charts to get a setting for the catapult.
Next, the plane is harnessed to the catapult.
Once everything's good there, we take tension, so I hit that bridle tension button, and that's when the shuttle moves forward and locks into that launch bar. That's when we go to military power. That's the pilot's signal to spool up power, start getting his engines ready.
Below deck, the crew sets the correct steam pressure. For an F-18, that's 520 pounds per square inch.
Once he's good, he gives that salute, and that's when I call salute final. Push our final ready button. That gets everything into the final status, ready to fire the catapult. From there, we just lift the lid and hit fire, and they go. Salute final. 520 clear forward. I got lights, no lights. -5. Thumbs, head steady, deck steady, no interval.
For this pilot, the next 2 seconds all depend on the coordination of his crew and some precise engineering.
Fire.
Hours of training, a highly skilled crew, and incredible engineering have all come together for another safe launch. It's an experience pilots never forget, going from 0 to 150 miles per hour in just 2.5 seconds.
Before your first catapult shot, You're anxious, you've been told what to expect, but it's way cooler than that. It's the best ride in the world.
The pilots continue to launch, relying on age-old steam to get their state-of-the-art planes safely into the sky. But this engineering is finally being replaced as Nimitz-class carriers are decommissioned. Their replacements, the Ford class, will be equipped with an all-new catapult system. Here, they test one on an 80,000-pound dead load. Instead of steam, it will use electricity to create magnetic power. This system will require far less maintenance, but deliver 30% more power with 20 times greater efficiency than steam. Meaning the new carriers will be able to launch bigger planes even faster. The Carl Vinson's 4 incredible launch systems means the crew can catapult a jet every 30 seconds to perform airstrikes over 400 miles away. That made America's Cold War adversaries nervous.
Would the Soviets ever use their formidable military power? Well, again, can we afford to believe they won't?
And suspicious.
Одна из реальностей современного мира.
On January 24th, 1982, less than 48 hours after the Carl Vinson began its first sea trials off the coast of Virginia, Russian spy planes flashed onto the ship's radar. The Air Force scrambled 6 jets. They located 2 Bear surveillance aircraft with cameras. Sent up from a Russian airbase in Cuba to spy on America's latest superweapon and test how fast they could launch planes. The American F-15s forced the Soviet planes to retreat. It would become a familiar pattern. In its first 18 months, the Carl Vinson had to deploy its planes 28 times to chase off Soviet surveillance aircraft intent on uncovering the new ship's secrets. 35 years later, the Carl Vinson's air wing remains its most effective weapon. The Nimitz class was designed to carry more aircraft than ever before. More than 70 split between the flight deck and the hangar bay. The problem is, how do you get a 60,000-pound aircraft up to the flight deck to take off? The answer? The biggest elevator I've ever seen. The USS Carl Vinson is a plane launching machine, literally. But there's another big part of an aircraft carrier's job. That would be the actual carrying. And as I'm about to see, lifting. The next engineering system we're going to take a look at uses a huge amount of brute force and sheer power to lift the aircraft on and off the flight deck. It's known as the elevators, and I want to show you how it works. On a Nimitz-class aircraft carrier, there are 4 giant elevators surrounding the aircraft hangar. So which elevator is this?
This is aircraft elevator number 3.
Man, it's a huge opening. It has to be big. It's designed to perform the near impossible. Lift fully loaded planes on and off the flight deck at high speed, while the vessel pitches in strong winds and high waves. The elevator is really just a massive 4,000 square foot platform, able to fit seamlessly into the hangars below and the flight deck above. How heavy is the whole platform?
The platform itself is 190,000 pounds.
That's a serious elevator. And how much can it lift?
It can lift 130,000 pounds
So, like, to give me an idea of, like, what is 130,000 pounds worth of gear? Give me an example of that.
It's either over 2 fully loaded F-18s.
Of course, this parking lot is often floating in a war zone, so it needs to do its lifting fast, and the Nimitz class could do it faster than ever before at 135 feet per minute. It's raised and lowered by cable, but they get their power from below decks. And another special piece of engineering.
So welcome, this is the lower level of the aircraft elevator machinery room. Down here is where we create all our pressure.
Those 20 cables that are lifting the elevator, they all end up right here at this anchor point. They wrap around this giant pulley system or sheave system, and this is controlled by the 3 pistons on the backside.
The cables get their enormous power and speed from a piece of engineering known as an accumulator. It's a device that can store energy and then release it on demand suddenly. Basically, the accumulator is a cylinder filled with compressed air. Then, hydraulic fluid is pumped in at high pressure, compressing the air even further. As soon as the elevator is engaged, a valve releases the pressure. The compressed air expands instantly, forcing the hydraulic fluid out of the cylinder to push a giant piston forward. That powers pulleys that lift the elevator and its 130,000-pound load 3 decks high in just 15 seconds.
It's amazing to think that all that pressure inside the accumulator, when it's released, it can lift that entire load on the elevator and the elevator itself for a total of over 300,000 pounds.
Like everything else on this ship, the elevator takes a lot of loving and greasing below decks and up top.
There's so much elements when you're out at sea, whether it's the salt water, the fumes from the planes, the debris, the wind coming in here, blowing things around. There's so much that can get into these locks that it needs to be cleaned on a very regular basis. This is like arts and crafts, Navy style.
The wear and tear is relentless. Time to get my oil can out again.
Yeah, it's interesting. The one thing that hasn't changed over centuries of sailing is grease and oil.
Constant maintenance and repair is critical to the effectiveness of this super weapon. The Carl Vinson was commissioned and launched during the Cold War, when America needed a ship that could respond to any eventuality and survive at sea for as long as necessary. But that takes enormous energy. America's biggest ever warship needed the world's most potent source of power: nuclear fuel. Hidden in the bowels of the USS Carl Vinson are some amazing technological innovations. The ship's nuclear-powered reactors. Of the 5,000 on board, only a highly specialized mechanical crew are allowed anywhere near it. That's how secret they are, and I'm definitely not one of them. What I have learned is that there are 2 of them. They heat water to generate the high-pressure steam that powers the launch system. They also turn giant turbines. Those spin generators to deliver electrical power to every system on the ship. The turbines also rotate 4 giant screw propellers to create more than 280,000 horsepower and drive the ship forward at 30 knots. These reactors can run the ship for 25 years. In 1986, the Carl Vinson was deployed in the Bering Sea, just 60 miles from the Soviet Union. Conditions here are some of the harshest in the world. Ice, fog, rolling seas make maintaining open supply lines almost impossible, and landing a plane treacherous. No aircraft carrier had deployed here since World War II. Until the Carl Vinson. Tracking the movements of Soviet submarines right on the Russians' doorstep. The Carl Vinson proved the Nimitz carriers were the most independent warships in the world, and that now nowhere was out of reach of American air power. Takeoffs and landings have been continuing throughout the night.
Oh, 5:30. Oh, I never want to sleep under a flight deck again.
I've seen and heard the extraordinary engineering involved in launching a plane. But that's only half the job of an aircraft carrier.
It's one thing to launch an aircraft off of a carrier, but it's just as important to make sure it lands back safely in just 3 seconds. To do that, we use some wire rope, hydraulics, and some pretty neat engineering.
In the early days, engineers used a cable connected to sandbags on pulleys to slow the plane and stop it. Most of the time. The setup is basically the same today. 4 2-inch wires run across the landing deck. They're called arresting cables and are designed to snag the plane's tailhook and bring it to a hard stop in just 2 seconds. But to stop a modern 30-ton jet, you need a lot more than sandbags. Engineers that designed the Nimitz came up with a solution. Like the catapult shuttle, the cables are just the visible part of a much larger system. It all happens just under the flight deck in the arresting gear room.
So one of the things I noticed is the flight deck, they get all the glory up there, right? I mean, the plane's coming in, tailhook grabbing the arresting wire, and smoke everywhere. For me as an engineer, this is the heart of how it really happens.
Yes,
you know,
it is.
I mean, this is amazing down here.
The engine operator is always monitoring to ensure that the proper temperatures, pressures, and the actual machinery is working properly.
Wow.
There's a lot of work that's involved down below decks, and it's very important that we do that job the right way. You never know what's going to happen, and pilots have to come home.
Yeah.
At its heart of the arresting system is another giant accumulator. Unlike on the elevator, it's not designed for speed. Instead, this accumulator is engineered to slow down a plane by creating resistance. The huge cylinder is filled with 300 gallons of hydraulic fluid and connected to a giant piston.
Let me show you. You can see under here is the piston. Most pistons might be 1/2 inch, 1 inch, maybe a 2-inch piston on heavy machinery. This piston is 18 inches in diameter.
When the plane's tailhook grabs the cable on the deck, it drives the piston forward, forcing all the hydraulic fluid through a small hole inside the cylinder. That hole is only 1/2 inch wide. The backup of fluid creates enormous resistance, enough to absorb 47 million foot-pounds of torque and stop a plane.
It works a little bit like this. Imagine this syringe system is your engine and your accumulator. As a tailhook grabs a cable on the flight deck, it's going to go through a series of pulleys and begin to push that hydraulic fluid through the piston into the accumulator. When it does that, it's going through a control valve, or in this case, a nozzle. This creates all the resistance you need to stop a plane from 150 miles an hour to 0 in just a few seconds. And amazingly enough, this engineering feat is able to recycle itself and do the exact same process in 90 seconds, catching plane after plane after plane.
It sounds simple in principle. In practice, it's a precise, high-speed, high-risk operation. For the trainee pilots, there are 3 critical stages as they prepare to land. On their first approach, the pilot will bring the F-18 toward the flight deck, but will then do a pass over the carrier. This is to help them get a visual of what it's like to approach a carrier at sea.
The first time I saw the carrier from the air, everyone says it looks small in a big ocean, and they're right. I saw it and was like, oh, I have to land on that tiny little rectangle.
On the second approach, the pilot hits the deck at 150 miles per hour, but doesn't attempt to engage the tailhook. Instead, the aircraft goes to full throttle on touching the deck and takes off again. This maneuver is called a touch and go. It trains pilots to abort a landing and quickly relaunch if they miss all 4 arresting cables. After the touch and go, it's time for the trainee pilot to earn their stripes by tackling a landing.
Landing an aircraft on an aircraft carrier is one of the most difficult things to do in aviation. The first time you see it from the air, it just looks like a little boat down there. And then you descend and you get down close to it, and it's massive. And it's intimidating to know you're about to go land on this thing.
As the crew prepares on deck, I'll be watching from below as the arresting system hopefully catches the speeding F-18s. He misses. The pilot goes to full throttle to relaunch and goes around for another attempt.
Right, so the tail hook hit the wire, but it missed it. It didn't pull it out. It happens. So right now you'll hear our topside guys, you can hear the footsteps. They go out and check that wire, make sure it's not broken, and they run back out.
Again, the pilot misses the cables.
Man, we're getting unlucky a lot tonight.
When we come in for a landing and we miss all the cables, we call that a bolter. At first it's frustrating, but you have to quickly put that away, compartmentalize, realize you're flying an aircraft, come back and land again.
The crosshairs on this monitor show the ideal approach position for an aircraft, and this pilot is spot on.
Wow. We caught one.
Soon, the trainees are nailing it every time.
3 on 3.
Wow. That's a lot louder when it's in your engine room, isn't it?
It is very loud.
So if the catapult shot is the coolest ride in the world, the stopping on the boat is kind of the opposite. People compare it to a car crash. Taking a very heavy aircraft going about 150 miles an hour and bringing it to a dead stop in the span of a football field or so.
Man, I think I need to get like a Richter scale in here. This room shakes so much. Yeah, I'm from LA, so I feel earthquakes a lot. I'm gonna guess it's about a 4.0, 4.5.
It's incredible to see the simple hydraulic principle I demonstrated operating at such scale and speed. By transferring the plane's energy from the arresting cable into the hydraulic fluid, the plane is brought to a complete stop.
How do you handle it when it's like a bigger plane versus a smaller plane?
It means that we have to adjust that valve to a different opening. So the heavier the aircraft, the smaller the opening, the lighter the aircraft, the bigger the opening.
Got it.
Got it. It's engineering genius in action. Systems like these have to work the first time, every time.
So the catapults and arresting gear are some very intricate but powerful pieces of gear. They have to operate with the timing of a fine Swiss watch. They have to be exactly the same every time so that we can launch those 70,000-pound aircraft consistently and safely every time.
That extraordinary engineering was put to the toughest test yet in 1996, when the United States once again took on Iraqi dictator Saddam Hussein. America wanted to use air power to hammer Iraq from the Persian Gulf. The perfect task for the USS Carl Vinson. It deployed as part of Operation Desert Strike. From offshore, its jets penetrated Iraqi airspace. Over one 90-day deployment, the Carl Vinson launched and landed over 8,000 flights, pounding Iraqi military targets with laser-guided bombs. Only a Nimitz-class aircraft carrier could have done it. And it would have been impossible without the extraordinary engineering behind the Carl Vinson's launch and landing systems. Operations like that are what this crew is training for. The pilots have one more day of evaluations to complete, and I have one final engineering innovation to uncover. A seemingly simple innovation that's right under my feet. It's my final day on board the USS Carl Vinson. The aircraft carrier flight deck has a reputation as the most dangerous workplace on Earth. With planes, aviation fuel, ammunition, and dozens of crew, there's a lot that can go wrong, and terrible consequences when it does. The most common accidents happen during takeoff and landing on decks crowded with planes, where crew have been killed or injured. The Nimitz designers wanted to make its flight deck safer than its predecessors, but they also wanted more planes and to launch and land them faster. What they needed to achieve both was more space. For years, carriers operated with a single flight deck. This is an overhead plan of the Essex class, the U.S. Navy's main carrier used during World War II. This meant that planes could take off and land, but not at the same time. This made operations slow, difficult, and dangerous. This problem was first addressed by naval engineers in the 1950s when they made a fundamental change to carrier design. The solution was an angled flight deck. By angling the landing area to one side, incoming aircraft could have a clear approach. That reduced the risk of plane crashes during landing operations. But it was the Nimitz that took the angled flight deck to a whole new level. At the front of the Nimitz-class Carl Vinson is the launch track with 2 catapults. Next to it, and at an angle, is the landing strip. It's offset by 14 degrees, 3 times more than previous carriers. That allows launches and landings to happen simultaneously, up to one every 30 seconds, making the flight deck busier than an international airport. Made of steel and coated with an anti-skid material, it's truly immense. Over 1,000 feet long and 250 feet wide. That's more than 4.5 acres, offering huge space for planes to land, take off, and maneuver more safely than ever before. But doing that still requires complicated choreography. That's managed by the flight deck handler.
This will let me know exactly how I set the flight deck up. We will also coordinate with navigation. So navigation will talk with reactor department and engineering if they have any high-speed runs, any turns, rudder swing checks, so that I'll know how to strategically place my aircraft.
You give them a window,
yes.
You tell them when they can come in, you got to coordinate with that flight plan that you've got.
Every day is different.
Wow.
Nothing's ever the same,
Yeah.
Chad. This is super easy.
How long you been doing it?
26 years.
26 years.
Yeah.
Wow.
Experience like that has been earned over decades of service in some of the most significant conflicts in American history. In October 2001, the Carl Vinson began the hunt for Osama bin Laden. The ship's aircraft were part of the first airstrikes against Al-Qaeda in Afghanistan. There were over 8,000 takeoffs and landings, nearly 11,000 flight hours, more than 2 million pounds of ordnance dropped on targets. All delivered from the deck of the Carl Vinson by air to the enemy's doorstep. Precisely what an aircraft carrier was designed to do. 10 years later, when Osama bin Laden was finally located in Pakistan by Navy SEALs,
they killed Osama bin Laden and took custody of his body.
His body was delivered to the Carl Vinson for burial at sea. That was done from this hangar bay, allowing the USS Carl Vinson to finish the job it started. It's the last day of evaluations for these pilots. As they make their final takeoffs and landings, it gives me one more chance to get below decks and see the arresting cable in action again.
It's almost like waiting to catch fish. You don't know if it's gonna hit your line or another one.
Not surprisingly, arresting cables take a real beating from the plane's tail hooks. Now, cable 3 is worn out. Crews train to kick into action and replace it with a completely new cable. The challenge, to do it before this plane lands. With just seconds to spare, the cable is replaced and the F-18 can make its landing.
When you complete your qualification, the LSO or landing signal officer, the ones grading us, they'll come up over the radio and say, "Congrats, man, you're a qual." So the training on the aircraft carrier is really the culmination of about 2 to 2.5 years of training.
The engineering on the ship may be 40 years old, but the constant maintenance it receives means it still runs like clockwork, time after time.
Believe it or not, that was catch number 105,527. And just about everything that you need to stop an F-18 in a couple hundred feet is right here in this room. American made, built to last.
The USS Carl Vinson has played a critical role in exercising American air power from the sea. It is just one of 10 Nimitz-class aircraft carriers, the last of which will serve until 2060. But already, the U.S. Navy has designed and built the first of a replacement fleet, the Ford class. The first entered service in 2017. 9 more of these new vessels are planned to create America's next $40 billion super carrier fleet. The Ford class is just the next step, building on the successful design of its remarkable predecessors like the USS Carl Vinson. This iconic, battle-proven supercarrier has shaped 4 decades of global history. It's a legacy made possible by extraordinary engineering.